Hello, viewers. Welcome to the lecture on linear algebra. So, in this lecture, I'm going to discuss a very basic and important topic, that is how we can reduce a given matrix into the echelon form or row reduced echelon form. And then I will let you know that how we can use MATLAB or Octave to find a echelon form of a given matrix. So let's start with that one. So first we share this. Okay, so now we are going to start with this one. So like suppose we have a system AX is equal to B. And in this system we have a matrix that is of order m cross n, and this X is of order n cross 1 and B is of order m cross 1. So this is a system of equations, and we want to solve this system of equation. Now you know that when the size of this matrix is small enough, then we can solve the system when we have m is equal to n. So let's start with the basic thing. Now this equation, so I can say that the system has solution if the right hand side vector, that is b, belongs to the column space of matrix A. So it should belongs to the column space of the matrix A. Only then we can say that this system is going to have the solution. Now, how I can say that one? Because you know that the matrix A is, I can write this as this is my suppose first column C1. Then I can make this system and write this one as a x1 first column plus x2 the second column of the matrix, and in the end, because my x belongs to n, so I will get my xn, and this is the nth column of the, or the last column of the matrix A. So you can see from here that it become the linear combination of the columns of the matrix A. And if I multiply AX, so it can be written in this form. So now if this is a linear combination of the columns of matrix A, and if this is equal to our B, then if B belongs to the column space of A, then we say that the system is solvable and this system is going to have solution. In other ways, we can say from this that now I will just take the help of matrix theory, and we can say that now we define augmented matrix that we generally represent by this one. So in this case, I will write my matrix A, and in the last, I will put the column B here. Now we say that the system one is consistent. Consistent means that we can solve the system if the rank of the augmented matrix is same as the rank of the given matrix. So in that case, we say that the system is solvable. Now, once the system is solvable, only then we can talk about. So, so I will start with this one. So let I consider that this system AX is equal to B, and this system is consistent. So I assume this one by taking the rank of augmented matrix, and I found that the rank of augmented matrix and rank of a matrix A is same. So I say that this system is consistent. Now, once the system is consistent, I am going to discuss what about the solution, whether this system is going to have unique solution or infinite many solution. So I will take the, so we can classify this into the three categories. So the first category, second one, and the third one. So the first category, I can say, let's take this one, and I say that we consider when m is equal to n. So in that case, our matrix A is a square matrix. So when the matrix is a square matrix and its rank is same as the augmented, so it is consistent. Now we take the, that how and when we can have the a unique solution or infinite many. Now you say that if rank of the matrix A is equal to n, then if the rank of matrix A is n, then definitely this matrix is going to be non-singular, and then in that case we are going to have a unique solution. So this is, we know that one. And now if rank of matrix A is less than n, then we're going to have infinite many solution. So this is the basic theory we know. Now if I come across the another thing is that when m is less than n, so in this case the number of equation is less than number of variables, because n is the number of variable and m is the number of equations. So in that case, like suppose I have a 2x plus 3y plus 4z. For example, I take like 2x plus 3y plus z is equal to 1, and y minus z is equal to 0. So this is the three variables, and uh, this matrix has a two equations, or this system has a two equation. So such type of equation we are going to have. Now let the rank of the matrix is r, and number of variables is n. So r is less than n, then anyway we are going to have a infinite many solution. Always we are going to have infinite many solution because r is always less than n. And how we can find this infinite many solution? Because the rank is r, so we have to choose. So we need to choose n minus r free variables. Like here, we have three variables. So one variable, suppose it's this rank is 2, so I have to choose one variable. So here y is equal to z, I'll put here, and then we'll substitute and then find the value of x. So n minus r free variables we have to choose. The third one is very important, that is when m is greater than n. So in this case, the number of equations are greater than the number of variables. So like we used to do in the least square methods. So in the least square method, the number of equation is quite high as compared to the number of variables. So in this case, what we're going to do is that if rank of the matrix A is equal to number of variables, that is equal to n, because m is greater than, then we have a unique solution. Otherwise, infinite many solutions. So this is the theory of how we can deal with the system of equation. Now the thing is that all these things are okay, but what will happen when our matrix A is very large? Like these, we talk about the big data. So whenever we have a large data, in that case, the given matrix we are getting from the large data, that is very very big or large in size. This matrix can be a thousand cross thousand. So in that case, how we can solve this system computationally? Because if your system is 3 by 3 or maximum 4 by 4, you can solve this system. But what will happen when it is a very big in number? Like you have a matrix A that is of order maybe 10 cross 20. How you are going to solve? So in this case, what we are going to say, now we are going to discuss a very important theorem, that is Echelon form. So in the Echelon form, what we are going to do, this is our matrix A that is of order m cross n. And now we are going to reduce this matrix or transform this matrix into another matrix. I call it A EA, the Echelon form. And this matrix is similar to, similar means look like similar to upper triangular, because the concept of upper triangle comes when the matrix is a square matrix. So that's why I'm saying that this is looks similar to the upper triangular matrix. Okay, and you know that when the matrix is a square matrix and it is upper triangular, then it is very easy to solve. For example, you suppose you have a system of equation, and that system of equation, I have the only values here like a, then a1, a2 up to an, then here it is b1, bn minus 1, c1, like this one. And we have these variables x1, x2, xn, and on the right hand side we have b1, b2, bn. Now you can solve this system because it is upper triangular matrix. If it is n cross n matrix, then from here I can write a1, b1, c1 like this one. I can go now by using the back substitution. I can find the solution of this by suppose last in the last I'm getting maybe I will take uh, h in the last one. So I can have h xn is equal to bn. So now I can find from here xn will be bn by h. So I am able to find xn. Now the if I go in this way, the previous one will give me xn minus 1. Then I will go further, and in this way I will be able to solve the system and able to find all these variables. Because this is possible because our matrix is a upper triangular matrix. Now what will happen, our matrix is not a square matrix. So if it is not a square matrix, then what we are going to do is we are going to reduce this one, and this is called the Echelon form. Because in computer also use the Echelon form to find out the solution. Whenever you use the computer or any language like C++, Fortran, MATLAB, Python, wherever you are doing your programming, and if you want to solve a system of equation, then the system of equation is solved using the Echelon form or the elimination methods. So this is we are going to discuss now. In the Echelon form, what we are going to do, that suppose A is my matrix. So suppose this is a m cross n matrix. Now in the echelon form, we start looking at first row like this one, and now first I will look at the first column, and then I will see that where this non-zero element is occurring, and I will switch over that swap this non-zero element. Suppose this is a non-zero element, so I will take this as the pivot element, and I will try to reduce all the elements below this equal to zero. Okay, then I will start looking at the next column. So in that column, suppose all the elements are 0, 0, 0, 0. Then I will look for the next one. The next column should be, suppose the next non-zero element is occurring here only. So I will leave this one because we have to go one further bottom to the first non-zero row. So in that case, I will suppose I will hit, so it is 0 here, but non-zero element is occurring here. Then I will make this all this element 0 and so on. And maybe in the end, I will get non-zero element here and all other values are there, but the element below this one should be 0. So this is the way we can find the echelon form. So echelon form, whenever it is achieved, then based on this echelon form, we are able to solve the system ax is equal to b. Now the things is there that how we can do this thing in the MATLAB or the Octave. So that is going, I'm using MATLAB or Octave. So MATLAB is a uh, software, so you have to buy for that one. But Octave is a free software, and it is just the copy of the MATLAB. So you can use Octave. It is freely available in the internet. You can download and you can start doing that one. So I will just start sharing this value or this MATLAB Octave. So I will stop this and then I will. This is Octave. Yeah. So it will look like a MATLAB, similar to MATLAB, but it is free of cost. And this is my Octave. So I can start with this one. Now, so suppose I have a system. So in that system, I have first I have to uh, input the A. Suppose I have the matrix A. So how I can make the matrix A? I am solving a system AX is equal to B. Okay. So now first I have to enter what is A. So A matrix, suppose I'm taking a, first I will start with 3 by 3 matrix. Let's take 3 by 3 matrix. So suppose I take the matrix 3, 4, 1, and then I will take minus 2, 0, 3, and then I'm taking 1, 2, 4. So this is the matrix, that is 3 by 3 matrix I'm taking. And if you enter, this matrix will appear like this one. So 3, 4, 1 is the first row, minus 2, 0, 3 is the second row, and third is 1, 2, 4. Now it is a 3 by 3 matrix. Now I'm taking the B vector that is on the right hand side vector I have to choose. So this vector is, suppose I taking 2, then semicolon 1, that semicolon 0. It means this is a just a column vector. Now suppose I want to find out what is the rank of the matrix A. So I will write just rank of A, and it is coming 3. So this matrix is a non-singular matrix. Now maybe I can um, write this matrix as So I need to find suppose augmented matrix. So I will write the matrix A B. A B means this is a augmented matrix I'm going to define. Now what I do, I will put the A here and B here, and I write like this one. So you can see that this is the augmented matrix I got. Now I can find the rank of this matrix also. A B. It is a 3, right? It means that this system is a consistent system and we are going to have the solution. And you know that this is a 3 by 3 system, matrix is not singular. So you are able to solve this system accurately and you're going to have a unique solution. So how you can find the solution, that is x, I can write x is equal to a backslash b, and that is going to give me the solution. So this is the solution for this system. Or maybe you can find the solution like y is equal to, you can also write inverse of a, this is same thing I'm doing here. So again the same solution you're going to. So either you can use this command a backslash b, or you can also write in this form. So now we are able to solve this system. Okay, so this is what we are going to obtain from this one. Now this is a very simple one. Now what I'm going to do is that let's take a matrix which is a very big matrix and which is also not a square matrix. So that is I'm going to take. So let's take this one. So first I will write, so I will clear this all this datas and I will write CLC. So clear the command window. Now let's take a matrix A, and this matrix is, I'm just taking 1 3 minus 2, then I'm taking minus 2, then 0, then 2, then 0. So I'm taking 6 elements in a row, then I'm taking 2 6 minus 5 minus 2 4 minus 3, and then 0 0 5 10 0 and 15, and then 2 6 0 8 4 18. So this is the matrix I got. This matrix is a 4 cross 6 matrix. Okay, and then I take the right hand side vector. So b I define like 0 minus 1 5 6. This is the right hand side vector. Okay, so this is my system equation, and now what I want to do, I want to reduce this matrix into the echelon form. First I will find out the augmented matrix A B. I just call it AB because I'm this combining these two. So I will write A here and B here, and this is my AB. Okay, so now I'm going to start the making this matrix into the echelon form. So you can see that the first element is 1. So take the I have to multiply the row R1 with minus 2 and add to the row 2. And that should be a new row should come at the R2 place. So what I'm going to do is that, see, if I write AB and suppose I write 2 and then comma and I write colon, so it means that we are taking the second row, and colon means all the columns I am taking. So second row with all the columns. So it gives me the second row. Or if I write AB and suppose I write colon here, and I write 3 here, it means we are talking about the third column, and this is the third column. So this way we can take the complete row and column. So so what I'm going to start is I am taking AB because I have to do everything at the second column. So I'm replacing this one. What I'm doing to I am taking minus 2 times multiply the first row. So first row I'm taking 1 and colon. So this is minus 2 into AB. So AB means the first row I'm taking, and then adding to AB second row. So I'm multiplying minus 2 with the first row and adding to the second row, and this effect is taking place at the second row, and I just this one you can see from here. So minus 2 plus 2 it becomes 0, minus 6 plus 6 that also becomes 0, and here I'm minus 4. So minus minus, that will be 4 minus 5, it will be minus 1, and so on. So you can see from here that a new row has happened. Now the same thing I'm going to do for the fourth row. So in the fourth row, I'm doing the same thing and fourth. So multiply minus 2 with the row 1, adding to the fourth row, and this effect is going to be on the fourth row. So this is my fourth row. Now we are able to finish the first step. So we are able to make all the elements below the first non-zero elementary 0. Now we look for the second non-zero entry. So second non-zero entry, you can see from here, it is not happening in the second column because it should be below the first row. But we got this value, non-zero value here. So this is my non-zero value, next non-zero value. So now I have to reduce all the values below this 0. Okay, so now what I'm going to do is that I'm writing AB, and first I am taking for the third one. So this is equal to, now what I'm going to do is I will multiply by 5 here to the second row and add to the third row. So I'm writing 5 star third row or second row, sorry. This is 2, this one, plus A, B, and I'm going to add it in the third row, and I got this value. So this you can see that this became 0. Okay, so this became completely 0 value here. Okay, now the same thing I'm going to do for the fourth row. So for the fourth row, I have to multiply by 4. So multiply by 4 means I have to multiply by 4 and add to the fourth row. I just did. So this is the value I got from this one. Now you can see that all these things are happening, but we got the 0 row. You can see from here that we got this 0 row that is, but what we are going to do, we have to take a swap of the third row and the fourth row. This is what we are going to do, because we have ultimately we are to take the all the 0 values or the 0 elements or the 0 row at the bottom. So this is what we are going to do here. So in this case, what we are going to do is that I have to swap the third and fourth row. So I will write AB. Now this is This is what I'm going to do. So I'm writing A B A B. So I'm dying that third and fourth row and all this column should be swapped with fourth and third row, and other things is same. So I just enter and you got this value. So you can see from here that first and second row is same. The third row has become the fourth row and the fourth row becomes the third row. Now, if you see from here, now this became a row the echelon form, because the first non-zero element is here, that is the first pivot. The second pivot I'm getting here, and the third pivot I'm getting here. So I can see from here that the rank of the augmented matrix is 3 and the rank of the matrix A is 3. And we can also verify this one. So just for the verification, I will find out what is the rank of A I have found and what is the rank I found for AB, that is also 3. And we can also check this value. So once we are able to reduce the given matrix into the echelon form, then now we got that this has a rank 3, and the number of variables you can see that is in this case are 6. So the three variables we have to choose just to get. So this system is going to have infinite many solutions. Now there is a inbuilt command to find out a row reduce echelon form. So in the row reduce echelon form is that, like, this is a non-zero pivot. So in the row reduced echelon form, all the elements in this column will be 0. So minus 2 will also be 0. Like here, this is the pivot element. So in this case, instead of minus 3, I will get 1. So that is called the row reduced echelon form. So there is a inbuilt command that is row reduce echelon form. And I want to find this one for maybe. And you can see from here. So what we get, one is there, okay, three is there. Then I have to make it one, and then the element above this is my 0. So this is what I made. And then instead of 6, I divide it by 6 and then make it 1. So this is 1, and then this value is 1 by 3. So you can see from here. So this is a row reduced echelon form. And you know that the row reduced echelon form is a unique for every matrix, but the echelon form you can have many echelon form. So this is the way we can find out the row reduced echelon form. So once we are able to find this row reduced echelon form and everything, then we can solve by the back substitution. So like here we are able to solve. So you can see from here this matrix, the echelon form, that I have x1, x2, x3, x4, x5, x6. So I can have 6x6 is equal to 2. So x6 is 1 by 3. So 0.33 is the value for x6. So similarly, we can find, because in this case we have to choose three variables as the free variables. Okay, so this is what we are able to do. Now I will tell you that in this form, the row reduced echelon form, using the Gauss Jordan, we can find out the inverse of a matrix also. So that to inverse of the matrix we can find similarly using the row reduced echelon form. So now based on this one, I am able to solve the system. You can have as big matrix as you want. Maybe I can find the matrix with 1, 2, 3, 4, 5, 6, 7, 8, 9 maybe. And then I can have matrix 0, 2, 5, 8, 7, 6. So this is 4, 5, 6, 7, 9, 6. And oh my god, so it might be 4 only. See the matrix I got, or maybe I can have the very big matrix. Okay, so this is a 0 0 matrix. So I can make this, and this matrix I just like row reduced echelon form. So this is a row reduced echelon form. I can find the rank of the given matrix. This is the rank of the given matrix, and based on that, the way we have done, we can first reduce the echelon form and then we can solve the system. So this is things we can wanted to discuss in this case. Now you can play with this one. Suppose I have a matrix, so I just uh, write CLC, and I will just write all the variable. So I just write the matrix A, and suppose I just take the same matrix 3 4 1, then I take -2 0 3, and then I will take 1 2 4. So suppose this is our matrix. So it is a 3 by 3 matrix. We have taken this one. Now I want to find the inverse of this matrix using the Gauss-Jordan form. So in the Gauss-Jordan form, we know that we find the inverse of the given matrix. So this one I can do very easily. So what I do is that first I will write the matrix which has the matrix A and the identity matrix. So I define just a new matrix B. So that matrix I define, first I'm writing the matrix A, and then I will write I. So I means the identity matrix and of the size. So size is, I know the matrix, the size is 3. So I will just write the size of the matrix A, and I will just write this one. So you see, I got the matrix B. So the first part of this matrix is 3 by 3, whatever the A is there, and this is my the identity matrix. Now what I will do, I can apply my Gauss Jordan form. Basically, what we are going in that one, we are reducing the matrix A into the row reduced echelon form, and ultimately this matrix, the identity matrix, will become the inverse. So this one, these things I can do directly by the, so I will write row reduced echelon form and of this B. You can see from here now the first three that become the identity matrix, and the last, the identity matrix became the inverse of this one. And you can also verify this one by taking inverse of the matrix A. So inverse of the matrix is A, this one, and this is same as this matrix. So by the help of the row reduced echelon form, we can find the Gauss Jordan, and then with the help of Gauss Jordan formula, we can find the inverse of the given matrix. Only thing is that this is applicable for a square matrix. These things we cannot do for the rectangular matrix. But we can have, now we are able to understand that how we can reduce the given matrix into the echelon form or the row reduced echelon form. Then we can play with this one using the Gauss elimination method. We can find the solution, or with the help of Gauss Jordan, we can find the inverse of the given matrix. So this is generally we can do at the basic level, and more we are going to discuss in the coming lecture. So I hope that in this way we are able to understand that how we can take the help of Octave or MATLAB to reduce the given matrix into the echelon form or the row reduced echelon form. So I hope that these lectures will be beneficial for you uh, in the way that you are, if you want to teach the students that how this row reduced echelon form or the echelon form can be done in the computer, then you can try these commands what I have just done here. So this will be beneficial for all the student also, and then you can continue with this one and you can go up to the higher level. So thanks for watching this lecture. Thanks very much.